In today's video, we will have a look at the implementation of the pricing framework for reinsurance. As you can see, the high-level structure in this screen. After having implemented and discussed exposure profiles in the last session, we will today focus on the generation of claims. And what you can see here on this screen is an example of a severity and frequency distribution based on the underlying profile. Welcome back to the MeshWeaver channel. Our goal is to help you to manage and understand your data. My name is Stefan, I'm here with Roland, and today we look into the sampling of the frequency and severity of claims based on the profiles which we have in the reinsurance. In generating claims, I think I will split into two parts, because the first is relatively straightforward. It's just generating frequency and severity. And then the second part will then be to also generate the development of the claims. Yeah? So this is then a little bit, let's say generating the development requires a little bit more work than just doing the frequency and severity. So we will use a separate session for this part. So here what we see is again the exposure profile which we looked at last time. And what I did for this exposure profile, this is the blue curve. So to each band which we have, I designed the exposure curve, and I'm using the MBBEFD distribution, and with the one parameter, so more or less which corresponds to the Y curves. So for lower bands, I use a low parameter, so around 1, and the higher up you go, you have a parameter which maybe goes up to 6, 7 or so. And this is part then, if you go back here to the market model, so this is specified in here. So I'm telling the market model how to, which curve to use depending on the size of the risk. And then this parameter goes into the severity model. This is more or less how it works. And if I now take for each band, I can calculate the frequency severity curve, so I can use a survival function for each band, and then I can aggregate the survival functions to get the overall frequency severity curve for the profile, and these are shown here with the blue curve. So this is basically what I expect. So this is the severity distribution of the whole portfolio shown as a survival function. Then when I sample the claims, of course I go it band by band, and I expect that I get something which then looks more or less the same. Of course there's some deviations because the number of claims is not very big. So in this case we have a frequency of 38, and in this sample I got a 38.4, and the actual simulation generated 38 claims. So it's pretty close. And you see here the 38 claims, how they're distributed, again in the log-log scale. So they follow more or less what we expect, so this looks good. But there's also quite some deviations. And so if I run the model multiple times, then you can see then the variation is quite big. So here you see the number of claims. So it's still the same, 38.4. One time it was 42, 41, 35, and so on. So in the average, we are close to the 38, but the variation can be quite substantial. What I also did, just out of curiosity, I was asking myself, what happens if I, instead of taking the actual exposure curve, if I say I have only total losses? So basically, which corresponds to a curve 0. So it's a total loss curve. And then, of course, I have larger claims, but then if this premium and the loss ratio is given, then I need to compensate by saying the number is lower. And this is shown here in these red curves. It's kind of an upper limit. So here the frequency is only 14 instead of 38. And then the curve looks here like this. So it's just gives also a hint to say you would expect that if you run the simulation multiple times, it should not be totally beyond this curve. So this is just for me to visualize a kind of upper range for where do I expect the variability to be. So this is more or less what I have done here.
To me, it looks very good because I think you want this variability. It also depends on the product. Not all the products react similarly to all the features. So it's exactly what you want to produce, a certain realistic variability and this looks like this to me.
Yeah, and I mean, maybe just to mention, if you just look at conventional exposure-based rating, what most of the people do, they use the blue curve.
Yeah, the average curve, yes.
It's just the average, but you can see, of course, the variation can be quite substantial. Yes. And if you have a generative model, then you can exactly also bring this variation into your model, which otherwise you're missing.
And especially also with non-proportional elements, it's usually not even so easy to say. So I noticed this when computing with interest rates and life products. Usually you cannot even answer the question, if I raise the interest rates, will my overall loss go up or down? Not even this is clear.
Okay, now this is just an outlook. So what do we want to do in the next step? And to do this, I just basically have been drawing here a very simple case of one claim and how it evolves over time. So what we see here is a reporting lag of 3 years. And I assume the information comes in at the end of this period, but the tool was not able to draw it this way. So basically here I have a line going from time 2 to up to 3, but this should be actually, it should be a step function here going up. And what we have, so let's assume there's a reporting lag of 3 years. I assume the claim is closed after 10 years, and we have 3 payments. The first payment of 100 in thousands is after 3 years, another payment of 200 at the end of year 4, and the final payment of 700 in year 10. So the total amount is 1 million, or 1,000 times 1,000. So this is the ultimate here. So the payment is clear. What is the green line here is showing the aggregate payments. So one of the aggregate paid amount, so 100, 300, and then 1,000. What we also have here is the incurred amount. So the initial estimate here is 1,500. Then in year 6, there is a new assessment of the claim, and here the estimate is for the ultimate is 1,200, so it went down. A year later, it goes down to 800. And then it stays there, and at the end, of course, it goes up to 1,000 because this is how the claim is settled. So this is showing the development of the incurred. And then what we can also do, we can take the difference between the red and the green curve. This is the outstanding amount. So this is what you need to keep in your reserves, what you expect that you will have to pay in the future. And this outstanding is just then the difference, and of course ultimately goes down to 0. Now I want to do some statistics. So of course we can use the actual payments and all the incurred adjustments and so on, but for the purpose of calibration, it's very difficult to handle with to do it with these objects. So what we do is, and this you can go to our initial discussion we had, and also the paper which we published where we describe this, how this calibration is working. So we take just some aggregate statistics, and basically what we do is the area under the curve, calibrated somehow. And this I've defined here. So this is all the information you need for a claim. So you have the date when the occurrence date, the reporting lag, closure lag. Then you have a tuple with payments, so the amount and the time or the lag, and then the same with the incurred. So all this information you need to describe a claim. This is more or less what we also showed in the anti-iterationship model. And then here's the relation between the incurred, which is the expected value of the ultimate at a certain point. And then this is, of course, they can decompose it into the paid amount, so what is already paid, and the outstanding payments, so this is then the expected payments in the future. Now, what I'm introducing here, I mentioned already the integral. So this is kind of a lag which I define at a certain point in time. So there's a variable here, time, and at any point in time I can define an incurred lag, which is defined by this integral here. Yes, the incurred, and the same also for the paid, which I have down here. Or if you have individual payments, you can also express it as a sum, or if it's the final, the ultimate at the time of closure, then there's in the ultimate lag which you have. So there is what we are using for the purpose of calibration. So because we have only partial development, so we maybe at the time the claim is submitted is maybe at year 5. So we only have information up to this point in time. We don't know what's happening in the future. So this is what we need to put into our calibration model here. So these lags here are estimated at any point in time as we move on. And of course, once the claim is closed, then this should not change anymore. So that's how it's defined. So that's why I'm using here the 1 minus this, and once the ultimate and is reached, then this value under the integral becomes 0, so you don't add anything anymore. So this is more or less the statistics we're using. And we can then also put it into a graph, which I did for the case above. On one hand side, you see the blue line, which is more or less the reporting lag. So it's 3 years, and then it remains constant, because once it's reported, it is reported, it doesn't change. The incurred lag is now interesting, because at the beginning, as long as I don't change it, it is the same as the reported lag. But because of the definition, if I increase it, then the lag is going down. It can even become negative. And here you see at the ultimate, it's below the reported lag. So overall, I have a favorable development in this case. If it ends up above the reported lag, then this means you have an adverse development. So you can immediately see in this representation, how is a claim? Is it developing in a favorable way or in an adverse way? Or is it more or less stable? In the case of the paid pattern, which is then always also put in relation to the incurred, there it is influenced by both. It depends on how much is paid, and it also depends on what is the incurred estimate. So in here, it increases, and the ultimate lag is then something about 8. So this is more or less the statistics we are using, and this is how the statistics evolve over time. So this is what we will then look at in the next step. So basically how to generate synthetic claims which evolve based on the given statistics. So we see here what we enter into the model are then the expected values for the different lags. So for the reporting lag, for the incurred lag, we also say what is the number of incurred adjustments. So above we have seen we've made the first adjustment here when we know about the claim, a second one here, a third one here, and the last one here. So in this case, there were 4 adjustments of the incurred and 3 adjustments of the paid. So this is also part of the statistics. Then for the paid, the same. We have the paid lag, the number of payments, and at the end the closure lag. So this is more or less how we describe any claim and what kind of statistics we are using, independent on when we make a payment or when we make an incurred adjustments. We just want to look at the statistics, and these statistics we can extract for individual claims, but we can then also aggregate the statistics for multiple claims per year. We can also aggregate it on a per time. So basically this is the kind of information we want to use for calibrating the model. Once the model is calibrated, then of course you don't need the incurred. The only thing you need is the cash flow, so the payments. So on a prospective basis, we don't need all this. Of course, we need to specify the model. So this is where the statistics is still helpful. We say what is the expected reporting lag, what is the expecting closure lag. So this is needed also for going forward, but for calibration purpose, we don't need it. So this is just to give a an overview of what we want to accomplish then in the next step.
So, I mean, it's not untypical information, right? So this is, I think, the big difference between what you are doing and what, say, most are doing is that you don't just take the average and you don't just calculate stuff with a mean, but you really generate these scenarios that give a bit of variability around the mean, right? So this is the main difference.
But I don't know if it's standard. I mean, so far I have not. Of course, the report, everything like this is clear, but I haven't seen any application where the lags have been defined in this way, or where they are actually also used for modeling purpose. You know? So maybe in some cases, people, they show some information for the claims, but I haven't really seen an application where it's implemented and used. So this is...
I have seen a lot of live models.
Yeah.
I think in live models it's more common. And I think you were mainly in non-live.
Exactly.
I mean, when I was with you, me as well, but afterwards, especially when we did all this IFRS, I started to look more and more into live models. And I think live models, they are more used to dealing with all these quantities.
Yeah. And maybe someone in the audience knows examples where this is or similar approaches are already implemented. Of course, we will be curious to hear about. So thank you for watching, and if you're still with us, don't forget to subscribe and to like us. We see us again in the next video. Happy weaving!